In this next series of videos, we're going to be introducing implicit differentiation. For that to make more sense, though, it's important to have a good foundation for the linearization that we've seen earlier. So let's go back to that idea, looking at a function f of x, which gives us our y value, and from that building a formula for tangent lines. Consider the function here, y equals e to the negative x. That's our exponential decay function, and the point x equals 0. Hopefully you have an image in mind as soon as that function is presented to you, and with the point selected x equals 0, also a point on that graph. Now think back to earlier work where we looked at tangent lines and see if you can quickly do the calculation for what the slope and the full formula of a tangent line at the point x equals 0 would be, and see if you can identify it in this list of functions to the side here. We'll give that a second and then we'll check in. All right. Our function is y equals e to the negative x, and the derivative is going to be negative e to the negative x from the chain rule, the derivative of the exponent multiplying in there. At the point x equals 0, we're going to have y of 0 equals e to the 0, and that's 1. And dy dx, a little cumbersome to write, so we write y prime. That'll be negative e to the 0, and that will be negative 1. With those two ingredients, slope and value, we can build our linear approximation, or our tangent line formula. We take the slope times x minus the point where we're referencing ourselves, which is 0 here, plus the value, and at the end of the day, we would most likely rewrite that as 1 minus x, or negative x plus 1. Looking down the list here, we see that a is the function that we would use as the linear approximation to e to the negative x at the point x equals 0. With that in mind, let's see how we can tackle some more challenging problems. Here is a classic circle, radius 4 in this case here, centered at the origin. And first question, can we define a function of the form y equals f of x that gives us all the points on this circle? Take a moment to think about that and see which of the answers here makes the most sense to you. All right, well, if we look at this and try to imagine it as a function, pick a value like x equals 2, we get a value for y at that point, but we also get another value of y at that same point. Another way to look at this is that this function or this graph fails the vertical line test, and that vertical line test is for functions. Or another way to say this is a function has at most one y value for each x. When we pick some x values here, we get two y values. That's a no-no for functions. So I guess technically we should put a check mark beside the no here. So this is a circle, and it cannot be described using a formula like y equals f of x. Now, having said that we cannot write this circle, all the points on it, as a formula y equals f of x, it does not mean there's no formula. This is a circle with radius 4, and you should have seen earlier in your career that if a circle is centered at the origin, it can be written as x squared plus y squared equals the radius squared. We can double check some points. 4, 0 satisfies that. 0, 4 also satisfies that. Negative 4, and also all the other points in between. If you're wondering why Pythagoras is in there, just a reminder that you can always define any points xy on the circle as this distance in x, this distance in y. Those are two sides of a right angle triangle, and the hypotenuse is always 4. So there's a perfectly good formula or relationship for the circle. It's just not in a y equals something form. If we try to do that, we end up with square roots plus or minus, and then we're stuck with multiple values of y. All right, so now we have our circle, and let's say we pick a point on there. Here we're picking the point 2 root 12, somewhat arbitrarily. Our question is, can we, in principle, without knowing how yet, but could we define a tangent line to the circle at this point here? Think about it for a moment, then we'll come back. All right. Well, if we look at this point, I think most of us would agree that if we draw a line like this, that would be the tangent line, up to some quibbles about how steep the slope is. But there certainly is a line that would exist that is tangent to the circle at that point. So absolutely, we should be able to create a tangent line at that point. The challenge is going to be, how do we achieve that, given that all our derivative skills don't seem to work immediately on formulas like, going back a page, x squared plus y squared equals 4. When we had y equals, we could take derivatives easily. Now that we have this new form, how is that differentiation or getting formulas for slopes process going to work? That's what we're going to investigate in the following videos.